Your heart is a remarkable pump. It works tirelessly, day and night, to move blood throughout your body. This blood carries oxygen and vital nutrients, and it carries away waste products. The process that allows this to happen is a repeating sequence called the cardiac cycle. Each single heartbeat represents one complete cycle. It is a beautifully coordinated series of events involving muscle contraction and relaxation. Understanding this cycle helps us understand how the heart sustains life with every beat. The cardiac cycle is divided into two main phases. Systole, the contraction phase, the heart muscle squeezes to push blood out. Think of it as the power stroke. Diastole, the relaxation phase, heart chambers relax and fill with blood. Both phases are essential for the heart to pump efficiently. Timing between them is critical for healthy blood flow and pressure. To understand the cycle, we must know the heart's basic anatomy. It has 4 chambers. The 2 upper chambers are called the atria. The 2 lower, more powerful chambers are the ventricles. One-way doors, valves, connect the chambers and guard the exits. Valves ensure blood flows in only one direction: tricuspid valve, mitral valve, pulmonary valve, aortic valve. The entire process is controlled by the heart's own electrical system. It sends signals telling the muscle when to contract and when to relax. We can see this on an electrocardiogram, or ECG. ECG shows distinct waves, the P wave and the QRS complex. Looking at electrical signals, pressure changes, and movement of blood gives a complete picture of heart function. Let's begin our journey through the cardiac cycle. With the heart in a state of relaxation, this is the start of diastole. During this time, the ventricles, the main pumping chambers, are completely relaxed after their previous contraction. Their internal pressure drops significantly. At the same time, the atria, the upper chambers, are filling with blood returning to the heart. The right atrium receives deoxygenated blood from the body. The left atrium receives fresh, oxygenated blood from the lungs. This sets the stage for the next crucial step in the cycle. Because the pressure inside the relaxing ventricles is now lower than the pressure in the full atria, the valves between them open. Tricuspid valve on the right side, mitral valve on the left. Once these valves swing open, blood begins to flow passively from the atria down into the ventricles. This is like opening a dam. The blood simply moves from an area of higher pressure to one of lower pressure. This initial rapid rush of blood accounts for the majority of ventricular filling, about 70 to 80% of the total volume. This phase is known as rapid ventricular filling. It is a passive process, meaning it does not require any muscular contraction from the atria. The blood is simply drawn into the expanding ventricles by the pressure difference created as the ventricular muscle relaxes. As the ventricles continue to fill, the pressure difference between the atria and ventricles starts to decrease. Consequently, the rate of blood flow slows down. This slower filling period is sometimes called diastasis. The heart is patiently and quietly preparing for its next forceful push. Following the passive filling of the ventricles, the cardiac cycle moves into a brief but important phase called atrial systole, also known as the atrial kick. This is when the 2 upper chambers, the atria, contract. This event is triggered by an electrical signal that originates in the heart's natural pacemaker, the sinoatrial node. On an ECG, this electrical activity is represented by the P wave. the contraction of the atria gives a final active push to the blood, squeezing the remaining volume from the atria down into the already mostly full ventricles. This atrial kick contributes the last 20 to 30% of blood to the ventricles. While the heart can function without this final push, especially at rest, it becomes much more important during exercise. When your heart rate increases, the time for passive ventricular filling is much shorter. The atrial kick ensures the ventricles are filled as completely as possible, maximizing the amount of blood that can be pumped with each beat. At the end of this phase, the ventricles contain their maximum volume for that cycle. This is the end diastolic volume, or EDV. Think of the ventricles as fully loaded and ready for contraction. The atria relax and begin refilling with blood from the body and from the lungs once again. The stage is set for the ventricles to take over and perform their powerful pumping function, the cornerstone of circulation. The atrioventricular valves are still open to allow this topping off, but as atrial contraction ends and ventricular contraction begins, pressures shift dramatically. The next phase will see these entry doors slam shut, an event you can actually hear. Section 4. Building pressure, isovolumetric contraction, and the first heart sound. Now we enter the first phase of systole, the heart's contraction period. This phase is called isovolumetric contraction. It begins immediately after the atria have finished their kick. The electrical signal has now traveled down to the ventricles, which is visualized as the QRS complex on an ECG. This signal tells the powerful ventricular muscles to begin squeezing. As they contract, the pressure inside the ventricles rises very quickly and steeply. This sudden increase in pressure immediately pushes the mitral and tricuspid valves shut. The closing of these two atrioventricular AV valves creates the first of the two main heart sounds. This sound is known as S1, often described as a lub sound. When a doctor listens to your heart with a stethoscope, this is the first sound they hear in the classic lub-dub sequence of a heartbeat. The S1 sound signifies the beginning of ventricular systole. During this specific phase, the term isovolumetric is key. Iso means same, and volumetric refers to volume. Therefore, this is a period of contraction where the volume of blood inside the ventricles does not change. This is because all four of the heart's valves are closed. The AV valves have just snapped shut, and the aortic and pulmonary valves at the exit of the ventricles have not yet opened. The ventricles are a completely sealed chamber, building up pressure to overcome the aorta and pulmonary artery. Think of it like opening a door that has a strong wind pushing against it. You have to push harder than the wind. Section 5, the main event, ventricular ejection. Once the pressure inside the contracting ventricles exceeds the pressure in the aorta and the pulmonary artery, ventricular ejection begins. The shear force generated during isovolumetric contraction pushes open the two final valves, the aortic valve on the left side and the pulmonary valve on the right. With these exit doors now open, the powerful ventricular muscles continue to squeeze, forcefully ejecting blood out of the heart. This is the moment when blood is sent on its journey to the rest of the body and the lungs. Blood from the left ventricle, which is rich in oxygen, is pumped into the aorta, the body's largest artery. From there, it will be distributed to your brain, organs, and limbs to supply them with the oxygen they need to function. Simultaneously, the right ventricle pumps deoxygenated blood into the pulmonary artery. which carries it directly to the lungs. In the lungs, this blood will release its carbon dioxide and pick up a fresh supply of oxygen, completing a vital part of the respiratory exchange before returning to the heart. The amount of blood pumped out from each ventricle during this single contraction is called the stroke volume. Not all the blood is pushed out, however. Even after a forceful contraction, a certain amount of blood remains within each ventricle. This leftover volume is known as the end systolic volume, or ESV. The efficiency of the heart's pumping action can be measured by the ejection fraction, which is the percentage of the initial blood volume, the EDV, that is ejected during this phase. A healthy heart typically has an ejection fraction of over 50%. This ejection phase has two parts: an initial rapid ejection, where most of the stroke volume is pushed out quickly, followed by a reduced ejection, where the flow of blood slows down as the ventricles begin to finish their contraction and the pressure starts to fall. On the ECG, the ventricles begin to repolarize during the later part of this phase, which is represented by the T wave. This signals that the main power stroke is coming to an end and the heart is preparing to relax and start the cycle all over again. Section 6, Winding Down, Isovolumetric Relaxation and the Second Heart Sound. After the powerful ejection of blood, the ventricles begin to relax. This next phase is called isovolumetric relaxation. Ventricular muscle relaxes and ventricular pressure falls rapidly. Very quickly, ventricular pressure falls below the pressure in the aorta and below the pressure in the pulmonary artery. That pressure reversal makes the aortic valve snap shut and makes the pulmonary valve snap shut. This closure prevents the ejected blood from flowing backward into the heart. The sharp closure of the aortic valve creates the second primary heart sound, S2. The sharp closure of the pulmonary valve also contributes to S2. This is the dub, in the familiar lub-dub rhythm of the heartbeat. Hearing a clear S2 shows the exit valves are working correctly, sealing the ventricles after their contraction. With these valves now closed, the mitral valve is still closed and the tricuspid valve is still closed. The heart enters a brief period where all four valves are shut. This is why it's called isovolumetric. Ventricular volume isn't changing. During isovolumetric relaxation, the ventricles continue to expand and ventricular pressure keeps plummeting. The atria have been passively filling with blood from the body and from the lungs, so the atria are now full. Atrial pressure is steadily rising as they accommodate that incoming blood. The stage is being set for the next big pressure shift. The goal is to lower ventricular pressure until it falls below atrial pressure, which will trigger the mitral valve to open and the tricuspid valve to open. This brief phase is crucial for setting up the next filling period. It's the transition from the heart's work phase, systole, back to its rest and fill phase, diastole. Isovolumetric relaxation ends the moment ventricular pressure drops below atrial pressure. At that precise moment, the mitral valve swings open, the tricuspid valve swings open, and the cardiac cycle restarts with rapid, passive ventricular filling. This seamless transition keeps the heart's rhythm uninterrupted. Section 7. A coordinated masterpiece. The full picture and its purpose. When we put all these phases together, we see the cardiac cycle as a beautifully coordinated masterpiece of physics and biology, passive filling of the relaxed ventricles during diastole. Atrial kick tops them off. Isovolumetric contraction begins, pressure builds. exit valves open, ventricular ejection, the powerful stroke to lungs and body. Isovolumetric relaxation, exit valves close, setting the stage for the next feeling phase. Every part of this cycle is linked. The electrical signals seen on an ECG, P wave, QRS complex, T wave. These are the conductors initiating mechanical contraction and relaxation at precise moments. The heart sounds S1, S1, S2, S2. Audible proof of valves opening and closing to ensure one-way flow. The lub-dub is the sound of life in motion. The purpose of this complex cycle is simple: maintain continuous circulation. The heart works as a dual pump. Right side receives deoxygenated blood. Right side pumps it to the lungs. Left side receives newly oxygenated blood. Left side pumps it to the body. Continuous one-way flow ensures every tissue gets oxygen. It also removes waste like carbon dioxide. In summary, filling during diastole, pumping during systole, governed by electrical signals, driven by pressure changes, controlled by 4 valves to ensure forward flow. Understanding this cycle is understanding how our body is powered, one heartbeat at a time.